Today we're going to talk about the language of chemistry. And what I mean by that is basically in science, sometimes it just sounds like we're speaking another language. So today we want to learn how to translate English into that language of chemistry and vice versa. So first and foremost, let's talk about what an element is. Now, an element is just a substance that's made up of one type of atom. Examples of this include iron, which is Fe, and iodine, which exists as I2, which means that there's two atoms in that element. We'll talk more about that in a second. So there are elements that can exist as monoatomic elements, which basically just means that it's made up of one atom in the world. And most elements are just exist in one atom, in the form of one atom. Now, these elements have a subscript of 1, and what I mean by subscript, it's this little number right here on I2. This says a subscript of 2. Now, even though they have a subscript of 1, we don't actually put it. It's kind of like an exponent. If we have 1 as an exponent, we don't actually write it. It's like invisible right there, but we know it's there, okay? So an example of this is this iron right here. There's no subscript, but I know that there's only one atom of iron because it's just Fe. There's just one of those. Now, diatomic elements are made of two atoms, and an example of this is this iodine up here. Because it has a subscript of 2, that means that there's two atoms in that element, that molecule, how it exists. Now, other examples of this are bromine, nitrogen, and chlorine. These are actually very important to remember. So there's a mnemonic device called Brinkelhoff, and this is how you remember which elements are diatomic. Now, it is very important to remember this because if, for example, we have oxygen in a chemical reaction, when you know that oxygen is reacting with something in a chemical reaction, you always have to write that oxygen as O2 because oxygen does not exist just by itself in the world. So again, Brinkelhoff, Br is bromine, I is iodine, N is nitrogen, Cl is chlorine, H is hydrogen, O is oxygen, and F is fluorine. So that's how you remember those diatomic elements. Now, polyatomic elements are made up of more than two atoms, and examples of this you can see on the right-hand side at the bottom there. We have phosphorus, which exists as P4, and sulfur, which exists as S8. Compounds are when two or more elements are chemically bonded. So examples of this are shown on the screen. Water is made up of hydrogen and oxygen. Ammonia is made up of nitrogen and hydrogen. Carbon dioxide is made up of carbon and oxygen. And hydrogen peroxide is made up of hydrogen and oxygen. So those are all compounds. So a molecule is a group of atoms that are covalently bonded. Now, the trick here is that all molecules are compounds, and chemical compounds is another how we call these things, what we call these things. But not all compounds are molecules. So in order to be a molecule, something has to have covalent bonds within that molecule. So examples of this are carbon dioxide and iodine. Those have covalent bonds within the atoms. Something that's not a molecule is Fe2O3. This has ionic bonds in this substance. And we'll talk more about ionic and covalent bonds later this year. Now, chemical formulas are a way to represent a substance that uses element symbols and subscripts. So for example, if I have 3 H2Os, I have 3 water molecules. The little numbers, so this 2 right here, under the H is the amount of atoms of each element in one particle of the substance. So this is called a subscript, and I've mentioned this word before in this lecture. I like to remember the name of this because sub is like submarine, which is under the surface of the water. This little subscript is under that element that it belongs to, basically. So this tells me that there's 2 hydrogens here. This subscript right here tells me there's 2 sodium atoms. This one tells me right here that there's 4 oxygen atoms. And then because sulfur doesn't have a subscript, I know that there's like an imaginary 1 right here. So there's only 1 sulfur atom. Now the letters here are the element symbols. They tell you the type of atoms in the substance. So I have hydrogen and I have oxygen. In this example down here, I have sodium, sulfur, and oxygen. And then last but not least, this big number right here tells you the number of particles. So this is called the coefficient, and this tells me that there's 3 particles of water. An atomic view is a picture that uses shapes to show what an element or compound looks like. So an example of this would just be water again. So you can see that I have one oxygen and two hydrogens right there. If I had three of those, I have three atomic view elements of, sorry, molecules of the water right there. Now, of course, this is a compound. There's three particles, so three molecules. The types of atoms within those molecules are hydrogen. There are 6 hydrogens because I know that in each water molecule, I have 2 hydrogens and I have 3 of total water molecules. So 3 times 2 is 6. There are 3 oxygens because within each water molecule, I have 1 oxygen, and 3 times 1 is 3. And then if I wanted to know the total number of atoms, then I count 9 because 6 plus 3 is 9. Now, chemical reactions are represented in equations. We call these chemical equations. The way that we write these things is reactants, and then an arrow, and then products, where reactants are your starting materials, so the things that are reacting together, and then the products are your resulting materials, so what you get out of that chemical equation, that chemical reaction. That arrow reads as either yields or produces or becomes. So the reactants produce the products. The reactants yield the products. That's how you read that arrow right there. And that arrow shows a change has happened and separates the reactants from the products. So let's do an example. We're going to translate English into this language of chemistry. So our example is that candle wax and oxygen react to make carbon dioxide, water vapor, light, and heat. So in the language of chemistry, or my chemical reaction, it looks like this, where C25H52, that's our candle wax. O2 is oxygen. Remember, oxygen is a diatomic element, which means it exists as 2 oxygen atoms. So that's why you have to remember your Brinkelhoffs, right? Because we have to know that if we have something reacting with oxygen, that oxygen is going to be O2. And I have 38 of those. The coefficient on oxygen is 38. And that reacts, so we can see that we have the arrow there, to make 25 carbon dioxides, 26 water molecules, because water vapor is just the state of that water, but it's still H2O. And light and heat are both energy. So we talked about endo and exothermic processes last week. Who can tell me, well, can you tell me if this is endothermic or exothermic? If you said exothermic, you were correct because it is letting go of energy. Energy is coming out of the system, exiting the system, so it is exothermic. Now, we also can put notations on chemical equations. You can see that there's like a little S right there, some G's, right? So what those are the states of those different compounds. So we have C25H52, that's a solid, that's wax. L stands for liquid. We don't have any of that in this example though. And then here, G stands for gas. So I have oxygen gas, carbon dioxide gas, and water vapor is also a gas. Now, another symbol that you see like this is this AQ, which means aqueous or aqueous. I've heard it pronounced both ways. That just means that whatever that substance is, it's dissolved in liquid, okay? Another thing that you might notice about this is that there's a little triangle above that arrow. What that means is heat is needed for this reaction to happen. So in order for this to happen, you have to actually light the candle, right? Heat is needed for it to happen. So let's answer some questions about this. So number 1, what are the elements in candle wax? Now remember, elements are just those letters, right? So in candle wax, we have both carbon and hydrogen. Number 2, what are the products? Well, I have carbon dioxide, water, and energy, right? The products are on the right-hand side of that equation right here. What are the reactants? Well, I know reactants are on the left-hand side here, so I have wax and oxygen as my reactants. Is CO2 an element or a compound? Well, that has to be a compound, okay, because we have both carbon and oxygen. Remember, compounds are made up of more than one element. And then O2 is an element because there's only one element in here. And then last but not least, how many atoms are on each side of the equation? Now, if we're actually counting up the atoms, we have to do that like we did on the slide where I showed you the atomic view of water. So what we have to do here is we have to actually add up how many carbons we have, plus how many hydrogens we have, plus how many oxygens we have to get the amount of atoms on the reactant side. So let's do that. So for reactants, we have 25 carbons, 52 hydrogens, and then we have 38 oxygens, oxygen molecules. But remember, in each oxygen molecule, there are 2 oxygen atoms. So we have to multiply 38 times 2. So if we add those up all together, you get 153 atoms. We're going to do the same thing with the product side. So we get 25 carbon plus 25 times 2 oxygens plus 26 times 2 hydrogens plus 26 times 1 oxygen, and you end up getting also 153. So this is really important to notice that you should have the same number of atoms on the reactants that you have on the products, because remember, conservation of matter says that, or conservation of mass says that mass cannot be created or destroyed. So it obeys the conservation of mass.